Hello and welcome to our IoT Builders YouTube channel. I'm Nenad Ilic, a senior developer advocate for IoT, and in this video I'm going to show you how I set up my Greengrass continuous deployment using GitHub Actions and OIDC on the Raspberry Pi Zero-W. This setup allows me to develop and test Greengrass components that publishes my Treadmill speed measurements to AWS IoT Core and save them in Amazon TimeStream using IoT rules. I'll also show you how I configured an Amazon Managed Grafana to visualize and analyze my running data. So I thought it would be nice to have a dashboard that tells me how much I ran and provides me with the current and maximum speed. And as Lord Kelvin wrote, I often say that when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever that matter may be. So what this means is that if you cannot measure it, you might not be able to improve it. So personally, I've been trying to increase my sprinting speed and have been training on a curved treadmill which doesn't have any motors or require a power supply. And one of the reasons I like running on this type of self-powered treadmill is that it allows me to run naturally on the balls of my feet. This motion creates a momentum to turn the treadmill belt by pushing your body forward, and the point of contact is significantly ahead of a center of mass. Thus, the experience of support is different than with other non-motorized treadmills and more similar to the one of running on the ground. Now let me show you my hardware setup. I've noticed that there is a magnetic reed switch that's triggered on each revolution of a conveyor belt, a conveyor drum. So I decided to wire it up and use it to measure my speed. To do this, I used a Raspberry Pi W with a battery module to simulate the reed switch impulses by providing a 1 Hertz signal. So this is for me in order to determine what is the relationship between the speed that somebody is running on a treadmill and the number of revolutions per second. So that's why I supply this with a 1 Hertz signal and then got a measurement by attaching this to a original display of 2.2 kilometers. I then tested other frequencies ranging from 2 Hertz to 17 Hertz and found that there was a linear distribution between number of revolutions and a treadmill speed with a conversion factor of 2.2. So this is what I did as well. So I did a test with 2 Hertz and so forth, and then got 4.4 kilometers per hour. So coming back to the original setup, I had basically a Raspberry Pi where I had a 10K pull-up resistor, and more or less every time a magnet crosses near the reed switch, I get a falling edge signal from 3.3 volts to 0 volts. Thus, the time between the falling edges gives 1 revolution of the conveyor drum. So, and once the magnet rotates further, the voltage rises back to 3.3 volts, and we have a rising edge that will stay there until the next cycle of the magnet's magnetic field interacts with the reed switch, as shown in the image. So now let's go to the code and more or less show how the setup has been done. Okay, so I'm gonna guide you through this example that we have. This example is located on the AWS IoT Builders tools and GGB2 home treadmill example. I'll put the link in the description as well. And as I mentioned, is inspired by this blog post, which goes in the details of like how the continuous deployment is set using the Greengrass. But since I'm using this on the Raspberry Pi, the first things needs to be done is to kind of install this GRE. So here I already SSH to my Raspberry Pi, which is more or less connected to my Treadmill, and I will add and make sure like to update and then install the GRE, since we will need it to run Greengrass. So now that's done, let's install the GRE. And now that's done. So the next step would be to more or less download the latest Greengrass by using this command, and make sure to export all the variables. Here the access key and the secret key is important, and then setting up the region. I use this home and then home treadmill. So home is the group, the Greengrass group, and then the home treadmill is the thing that's going to be used. And then more or less just running this command. So I already done that, so I have the this installed. And the next step would be to set the CD using the GitHub actions. As I mentioned, this is the best way to do it is just to follow the instructions over this blog post, but I will cover this here, more or less how it looks like in this repository. So here I did specify my component name, the Greengrass component name, to be this one as my Treadmill. I use the EU West 1 as a region, and then the working directory reflects the directory that's over here. And then further along, this specify what kind of job is going to be, and then what steps are going to be ran, and so forth. Installing the Greengrass GDK, which is the Greengrass development kit, and then kind of building and publishing the component that's going to be created out of this one, and then making sure that the right version and all of that is exported, and at the end creating the deployment. So in order for this to run, we need to do something beforehand, and that is first to create this OIDC role. This is done via the CMO file. It's a simple with a simple CloudFormation command, and then to add this role as well. This role specifies what the more or less the GitHub actions can do, and you can see that it kind of accesses the Greengrass thing group, and the account and the component name and so forth. So all of that is set up in here. So those are the two prerequisites that need to be done in order to allow the GitHub actions to work. So coming back to summarizing again, number one is installing the Greengrass with a specific thing group and a thing name on the device. And the second one is to more or less first add the OIDC provider and the OIDC role, and then have that GitHub actions as such. What this will do is it will allow us to have something like this. So once we kind of push new changes, the component will be published, and then it will be deployed. So how does this look like? So in this GGV2 home treadmill, we have the requirements which are going to be installed on the device. In this scenario, it's only the AWS IoT SDK. We have the recipe. The recipe specifies what are the artifacts and what is the life cycle of the component, and then what permissions does it have. So in this scenario, the operations that this component is allowed is to publish to the AWS IoT core, and then the resource at which, or the topic at which is going to be published, is going to be home treadmill speed, since this would be publishing the speed measurements. The artifact is packaged by the GDK, and you will see how that is done later, and it's pushed to the specific S3 bucket, And as I mentioned, this is the life cycle. The life cycle is once the component is first pulled down, and then the installation step is done, which basically installs the requirements that we saw earlier here. And then we have the run script, which is just running the measurements.py. So this is the GDK config, which tells like how this will be packaged and pushed. And then we have the deployment JSON template. This deployment JSON template is listing all the components that are going to be deployed on the device in this into which group. And in this scenario, we only have one component with a certain version that requires as a dependency to have Nucleus installed. And then, yes, defining also some kind of deployment policy in terms of like rollback and how this is done. The group to which this is deployed is the home group, as you can see it here from the IRN. So all the devices that will be part of that group will have that deployment. And then finally, coming back to the measurements. So in here, this is more or less what the Python script is doing. We have a bunch of things imported here. The most important one is the Raspberry Pi GPIO, and some collections. I will explain why this is needed afterwards. And then we will have the AWS IoT Greengrass IPC, which we will be using to communicate to the AWS IoT core. So the GPU that the Treadmill is connected is based on the diagram that we talked about, is the GPIO 18. And the conversion factor, again, this is what we mentioned earlier in the presentation, is 2.2, which kind of like allows this to convert the number of revolutions per second to the actual kilometers per hour that the person is running on a treadmill. This is the start time when the measurement starts, and we will be averaging this over 1, 2, 3, 4, 5 measurements. So we will get 5 measurements, and then we will be averaging those so that we don't have too much spikes. Here we are just creating the IPC client to kind of talk with Greengrass, defining the topic, as I mentioned, the home treadmill speed, and using the Atmos ones as a quality of service. So more or less, we are starting with the GPIO setting up. We are looking for the falling edge. That's where this callback will be triggered. So each time we go into this falling edge, the callback will be triggered as defined here. And we then go into the loop. We are testing for if there is an activity or not. If the activity is greater than 1 second, we are saying like, okay, this is something that there is most likely nobody running on the treadmill, and we are adding the 0 kilometers per hour measurement to our speeds list. And then calculating here the average speed, which is basically the sum of those and divided by the number of measurements that we have. So in this scenario, it's going to be always 5. And then if average speed is greater than 0, we're kind of logging this and then publishing this to the specific topic. This is the JSON, how this looks like, its time and the average speed. And more or less, we are kind of like preparing that payload and actually doing the publish here, and then just waiting for the future results. And that's it. And then this loop is called each 500 milliseconds. So that is more or less what is this doing. So the callback is just measuring the difference between the start and the elapsed time. So we are resetting the start time each time we are coming in here, and then we are monitoring how much is time has been passed. And then using the conversion factor, we are kind of just dividing this to make sure that we are getting that speed. And then we have a kind of a noise in scenarios that the speed is greater than 36 kilometers per hour, which is not able to measure this through. to this treadmill. We are kind of discarding those because that's probably noise due to different things that can happen on the line. And then if that's not the case, then we are just adding those, appending those speeds to our speed list that we will be using for the calculating the average afterwards. So that's more or less it. So basically, once a new change is made to this file or anything in the repository, then the actions are triggered. As you can see, there is each commit that basically triggers this, and then the component is published. So basically setting up the job. So everything that we saw earlier as the steps are here, and then component is being deployed. So that is it. The next part, like once this is done, we need to make sure that the time stream database is created, and then that all of those measurements are routed to the time stream database. Because afterwards, what we will be doing is we will be using the Grafana to kind of plot those measurements and get those averages, and I will show you how that looks like later. So in here, in this repository, we have the CloudFormation folder, and in that folder, we have a time stream YAML. This is a CloudFormation YAML file that describes, first of all, how the rule will look like. So we can select speed from home treadmill speed, so that the messages are published here where speed is greater than 0. And then make sure like all of that that is taken to be put in a specific database in the table called measurements. So in order for this to work, first we need to make sure that the Amazon time stream table exists. This is more or less the way on how we create one, and then that the database and the table as well. So here we're creating the database, and here we're creating the table. And then we will have a role that allows us to do this. So this is a role that allows the rule to be executed and then put into the time stream. So it has allow for the action time stream write records. So more or less, that is what needs to be done. I already did this, so this is the command that will deploy that specific time stream YAML, and this is what I have here. I've created, and then the resources that are created are listed here, as I mentioned. So the DB, the rule, and the table, and then the role. So that's basically what this is doing. And then secondly, we need to make sure to create the role for Grafana, because we will be using the Amazon Managed Grafana. And in order to do this, this is located here. So we have the Grafana role, which more or less is having a read-only access to access the Amazon time stream database that we created earlier. And the command to do this is more or less provided here. So this is the command. This is the command that creates the role. And then we will be using describe stack to get the Grafana role, which more or less we can also get from here. If we look at the stacks and then Grafana role, as the output, we will get the workspace role. So this is the role, and then we will need this in order to come here and then create a workspace. So we'll be using the AWS CLI again to create the workspace. So all of this that I mentioned, this is run outside of the Raspberry Pi. So this is run on a machine that can be used for doing the development. And then once that is done, we should have a plain Grafana, which more or less, this is now having the dashboard already, but we should have the plain Grafana running. And in order to kind of add the dashboard, there is a dashboard.json file, which we can just copy from here, which has all the queries and everything needed, and more or less go and create the dashboard, and then go here and then just import this JSON. If we say changes, that should be something like this, where then we can see the speed in real time. We can see the latest speed in real time, maximum speed and average speed. And then I can then show you the demo on me running what information we'll be seeing here. Now go back to the running. Okay, as you can see here, I'm stepping on the treadmill and then going slowly, and you can see that the speed is increasing to 9.64 kilometers per hour, and then slowly increasing to 11. Underneath we see that the maximum speed was 20.5 kilometers per hour, and the average speed that I ran throughout this course of a couple of days is 8.61 kilometers per hour. And here you can see that in here that I'm increasing my speed, so it's going from 11, 12 to 14 now, and I think I will reach the speed of about 7 kilometers per hour. And at that point I will stop. So after this it will take some time for the speed to drop down, since we are averaging, and now you can see that it's went to like 1 kilometers per hour. Okay, that's it. Thank you for your time. This was quite an interesting setup that I'll be using personally, and in case you have any questions, feel free to reach out or on other social medias as well. Below you can find the link to the mentioned blog post, but also you can follow our IoT Builder page using the QR code. That's it for today. Bye.